So Rosemary works for owns a company, I guess, Ellexus, and we kind of partnering a little bit with Rosemary because Rosemary provides these products that help us analyze I/O workloads. So as I said, we can cover a spectrum of workloads in reasonable fashion, and some particular workloads we do particularly well at. And so we were interested in working with Rosemary to find those workloads with minimal effort.
Thank you very much. I'm going to present to you a use case where we were looking to answer the question, do I have small IOs? Just a quick introduction to who we are. So James has already introduced who we are a little bit. Ellexus is the IO profiling company. We work with a number of people in HPC, including a lot of people who don't think they are doing HPC, but they are. All of our customers have one thing in common, that's lots of data and lots of really, really complicated applications that have to access it. So the tool that we use for this particular case study is Mistral. This is a tool that we developed to do very, very lightweight I/O profiling. So it's sufficiently lightweight that you can run it all the time. This wasn't the way that we were running it in this case. It's very easy to attach to your application. As you can say, you just run Mistral and then your normal command. And depending on what you've asked Mistral to look for, when you exceed a limit that you've set, Mistral will send you an alert. So in this example, job 42 has exceeded a limit of 500 megabytes per second to share Scratch. Obviously, that's a very simple bandwidth limit, but you can set it up to look for all sorts of things. And in this case, we were looking in particular for small IOs. So this case study was looking at a genome pipeline. Genome pipelines, show of hands, how many of you work in life sciences? Yeah, a few hands going up. So genome pipelines are known for doing very small IOs, partly because of the nature of the data, but also because of a lot of applications that have been developed over the years and are very hard to change. The pipeline that we picked is a publicly available pipeline. It's actually been very well optimized in lots of different ways, but not in the area of small IOs, as we discovered when we had a look. We weren't looking at seeing how it ran on a particular system, so we just threw the most enormous system. The specs here, 64 cores, 250 gigabytes of memory, far exceed what you'd need to run this particular pipeline. But we wanted to make sure that it wasn't constrained by any limits on the system whatsoever. It's the only application we ran on this system. It's publicly available as a Docker image, so very quick to set up, and we just wrapped it in Mistral. So, as I said, we're looking for small IOs. With Mistral, you just you say how often you want the data. We said every 60 seconds, so we could see how the IO profile changed over time. We looked at a few other metrics as well, but these were the most important ones. So here we've got the rules for read. Here we've got the rules for write. We split them up into different sizes. So 1 byte. 2 bytes to 2K, 2K to 1 meg and 1 meg plus. That's for each operation. So obviously the combined amount of IO would be much more than that. And we set the alert to trigger as soon as you did 1 byte. So as soon as there's a single IO operation, this rule will trigger. So we'll get every minute, if there was any IO at all, we'll get an alert telling us what it did and how much. So the pipeline ran for 10 hours. So it's quite a beefy pipeline. If you want to know more about the application that we ran, Eric, one of our engineers, is in the audience. He'll be around at the show later, so you can catch up with him and ask him lots of difficult questions if you want. Because we did what we call a kitchen sink contract, there was around a 20% overhead from Mistral. What we found was that in general the I/O was good. We didn't see any crazy patterns in the metadata or anything like that. But as expected with the genome pipeline, lots and lots of small I/Os. So this is a summary of the 1 byte reads. So as you can see, there were this is a period of about 10 hours. So this is sort of 10 minutes to 5 minutes. These 3 spikes with represented most of the 1 byte reads. There were 857 million in total. We had information every 20 seconds, so nearly 14 million in that 20 seconds. That's approaching a million per second. So really huge amount of I/O. And we looked at Mistral tells you where the I/O is coming from. It samples one of the results, and we found it was coming from an R library read table. So a completely normal, totally sensible library to use, but it uses 1 byte reads and writes in its implementation. Similarly here, 1 byte writes. This is a period of about 40 minutes, where it was doing a million per second. For those 40 minutes, so massive load on the system. 3 billion 1 byte writes over the course of that run. So here is a summary showing a few more of the slightly larger reads and writes. So I've left the other sizes off because the amount of I/O was negligible for the larger sizes. But you can see the bulk of although there were a lot of 1 byte reads, it actually constituted only a gigabyte of data, which is in genome terms not a lot of data. There was nearly a terabyte read in the 2 byte to 32K range. That was at an average of 700 bytes per read. And of course, that doesn't mean that there was a terabyte of data to read. We record if you read data over and over again, we record it again. I think in this case the BAM files and that the genome was using were just a few gigabytes, but they can, as we saw in James's talk, they can far exceed hundreds of gigabytes. In much larger applications. So you can imagine if it's reading a terabyte in this case, how much it reads in those cases. And the same for the writes. Most of the writes actually constitute only 3 gigabytes of data. So it was these 500 million slightly larger writes that was the bulk of the data. So a massive mismatch in the operations versus amount of work going on. So in summary, you can very, very easily discover your small I/O. If you're doing genome work, you probably do have small I/O. We've done some other work profiling applications in other sectors, and we found it's not quite to this scale, but it is pretty similar. Basically, if you haven't done I/O profiling on your application, you're probably doing small I/Os. If you are doing small I/Os, you should probably think about using IME, because that's a huge amount of wasted performance on the storage and the compute if you're not optimizing for that use case. So thank you very much. I'm not able to stay right to the end, but if you want to know more about this, then you can catch me at the DDN party later or email me. My email address is not hard to guess.